Okay, so I'd like to welcome you all to another edition of Quantum Fluids in Isolation. So I'm very happy to introduce Professor Simon Trebst here today. So Professor Trebst got his diploma in physics from the University of Bonn in 1999, his PhD in physics from the University of Bonn in 2002, and he was a postdoc at ETH Zurich from 2002 to 2005. And then he was a research scientist at Microsoft Station Q from 2005 to 2011. And from 2012 to present, he's been a professor of theoretical physics at the University of Cologne. And today he'll be talking about topology and supersymmetry. So please help me in welcoming, either by unmuting yourselves and clapping or by clapping virtually, Professor Simon Trebst.
Thanks, Joshua, for the introduction. Yeah, so it's a pleasure to be back in Boston and at least virtually, and talk about a project about topology and supersymmetry. And before we start doing so, let me say, talking about quantum fluids, that I went under, experimentalist this past weekend and, played with, soap liquids and soap ice on my balcony. And if you do make it to the end of this talk, you will see the video of, this soap bubble freezing over. But that's for later. So that's the soap liquid. We will mostly talk about spin liquids in this talk when we talk about liquids. But let's get there. Let me first, say, with whom I actually did the work. I will talk about two projects, both of which have been pursued by my PhD student, Jan Attic, who's actually in the audience. And one of these two projects we did in a very nice collaboration together with Michael Waller and Cristiano Bocciaduri, who's also here, over the past years. So I will talk about topology and supersymmetry, and I will start in a very different place. I will start with topological mechanics. So the growing field of systems where mechanical systems show features that we know from topology, and let's see how that actually works, and then work from there. So the field was kicked off by a very nice paper by Charlie Kane and Tom Lubensky in 2014, who explained the following. You look at a lattice, so you look at a system of masses and springs, connecting these, and you're particularly interested in so-called isostatic lattices. So what's that? It's a lattice, where the so-called Maxwell relation, so the difference in the number of degrees of freedom that you have in your system and the states of self-stress cancel exactly. So so this difference here is exactly zero. So we can actually calculate this for a lattice geometry, where we talk about sides and bonds as the spatial dimension times the number of sides minus the number of bonds. Because every side, so every mass can wiggle around in all the spatial dimensions, and bonds, which are rigid, constrain this motion. So so let's look at lattices that are static. So which have this condition that this Maxwell relation comes out to zero. If you go to lattices whose coordination number is 2 times the dimension, you will get an isostatic lattice. So the Kagome lattice in 2 dimensions or the Pyroclo lattice in 3 dimensions are such examples. So having this isostatic condition means that these lattices are on the verge of mechanical instability, and they're rigid, but as you will see, they will allow for floppy modes. So masses at the boundary, that you can actually excite and move around. And probably the most well-known example of that is actually this mechanical SSH chain. So that's an example of a one-dimensional system, which has 2 bonds, and as such is also exactly in this isostatic regime. And you can build such a isostatic chain, from Lego, and one of my students, Jan, who's here, has actually done this. So I will take the benefit of showing you this, and I can explain what I mean. So you see this is a system which in the bulk, so in the middle of the chain is rigid. So I cannot move anything here. But if I go to the boundary, I see that here on the boundary, there's a floppy mode. So there's something that I can actually move, and I can actually move this through the lattice, so that's on the other side, yeah. And then everything in the bulk is again it's rigid, yeah, and also here on the other boundary. So there's exactly one soft mode, one floppy mode, that is present in this one-dimensional SSH chain, yeah, built as a mechanical example. You can also do this in 2 dimensions or higher dimensions, yeah, and there are beautiful examples of this being done in the group of Sebastian Huber at ETH Zurich, who really built systems of pendula. So here we see the pendula hanging from the ceiling, heavy masses here. If you look from the top, you can see that there's some intricate way of having these pendula oscillate. And then in this 2-dimensional system of pendula, you can do something that we know from topology very well. If we excite here on the right boundary a mode, you see that these masses will start to move, but actually only on the boundary. Yeah, so the system remains rigid in the bulk, and you see that actually something is moving around. Yeah, so that's an edge mode that travels the boundary of the system and makes it all the way around. And such gapless modes at the boundary of a system to condensed metaphysicists immediately bring the idea of topological insulators, and that's exactly why this field is called topological mechanics, because of a correspondence between these mechanical systems and what we know from electronic systems. Yeah, so topological mechanics works with a correspondence principle, and let's actually see how that is formulated. Yeah, most often you will find it formulated as a matrix correspondence. So you say the mechanical system is described by Newton's equations, that determine how these pendula or mass points move, and you do this by by describing this Newton's equation via a dynamical matrix that tells you how these movements are done. Yeah, if you take the square root of this dynamical matrix, of this Newton's equation, you end up with an equation that we identify with an electronic system. That's a Schrödinger equation. Yeah, where in the Schrödinger equation, this dynamical matrix, ends up, in this 2x2 block diagonal matrix as off-diagonal terms. And this Hamiltonian, which is in symmetry class BD1, if you discuss these things in terms of symmetry classes, a free fermion Hamiltonian that you can solve, and that describes the electronic system and potentially some interesting topological state. And if some interesting electronic system, you can construct this way, the other way around, the dynamical matrix of a mechanical system, and then discuss how to implement this in terms of pendula, as we have just seen. This is example of Sebastian Huber, where he shows us how to construct a topological insulator, a bulk gap state, with an edge mode on the boundary. Yeah. So in this talk, I want to discuss this correspondence in terms of supersymmetry. Yeah. So you might say, oh, you just said it already. Yeah. So you said the Hamiltonian has the quantum mechanical Hamiltonian in this matrix correspondence is in symmetry class BD1, and as such has a supersymmetric form. But we want to be way more explicit than that. We really want to discuss this connection in terms of degrees of freedom, which are bosonic on the mechanical side and fermionic on the electronic side, and use this quantum mechanical idea of supersymmetry as it was first introduced in high energy physics to discuss topological mechanical systems. Yeah, so that will be on the menu for the first half of the talk, and then we will use this concept for more complicated states later on. So let's talk about supersymmetry in a stringent way, and so the basic ingredients will be bosonic and fermionic degrees of freedom, and those we want to connect. And the way that we do this is by introducing a supersymmetric charge operator. Yeah, so that's this operator Q here, which connects fermionic and bosonic degrees of freedom, which are written here in creation and annihilation operators. Yeah, so you can destroy a boson, you can create a fermion, and in between, there is a matrix, and that can be an arbitrary matrix, and this operator, this non-Hermitian, SUSY charge operator, is key to our construction to make a correspondence between a model of bosons and a model of fermions. And how do we do this? Well, we construct from that charge operator a Hamiltonian. So so we generate this supersymmetric Hamiltonian by writing down this anticommutator of this charge operator, and then we get a Hamiltonian that can immediately calculate. It looks like this. So it has a fermionic and a bosonic part, which by construction, by just this very step that we have done here, are isospectral quadratic Hamiltonians. So they are quadratic and they are isospectral. So that means that if you look at an energy spectrum, you will find exactly the same spectrum for the bosonic part and for the fermionic part. And it is this idea, that underlies, of course, the topological mechanics idea. And now let's formulate exactly how that works. So when we talk about topological mechanics, we talk about phase space coordinates. So we are somewhere in coordinate space Q, and we have some momentum P. And those are the bosonic degrees of freedom. Now these are bosonic degrees of freedom which are real. So these are real bosonic degrees of freedom. So we have an anticommutator like this. So if you want to connect those real bosons to their fermionic, their supersymmetric fermionic counterparts, they have to be real fermions. So what does that mean? That means that you're actually dealing with Majorana fermions. So the most natural thing, on the topological mechanics bosonic side, is connected on the fermionic side, with some Majorana fermion degree of freedom. Okay. So now let's write down the connection between these bosons and fermions, as we just said. So we have to write down this supersymmetric charge operator that connects the bosons, so P and Q, to fermions. And because we have two types of bosonic operators, we will also end up with two types of fermionic operators. So we have these gammas, gamma A and gamma B, which are type A and type B types of fermions. And
sorry, Professor, can I ask a question?
Absolutely, that's what we are here for.
So is there a simple reason that the superpartners of the real bosons has to be real fermions?
Yeah. So as I said, so the most natural thing is to do this. What it will do is it will ensure that all the symmetries that we will want to have. So time reversal symmetry. These things are all very well defined. And on the way, going back and forth in this supersymmetric way. Of course, we know that we can, write, real fermions in terms of complex fermions. So, you can do, one more step if you desperately want to talk about complex fermions. And we also know that many of those things that we will discuss in terms of spectra, are just free fermion spectra. And then, the difference between real and complex fermions will boil down to the presence of particle hole symmetry or not in these spectra. So where exactly in these spectra we will sit and what we will consider interesting in that spectrum. So bear with me, and you will see how that becomes interesting in just a second. Okay.
I see. Thanks.
So okay, so we have these two type of bosons, P and Q on the one side. We connect it to fermions on the other side. And in writing down this supersymmetric charge, we have started to define this arbitrary matrix R in some peculiar way, and let me show you how. So this the way that we have written this down, that we connect P to gamma B and Q to gamma A, encodes this block diagonal form, where there's some arbitrary matrix A here, and there's an identity here. Okay, so let's see what that actually means by constructing the supersymmetric Hamiltonian from this SUSY charge. So we've seen that it works like this. So we do this anticommutator of Q and Q dagger, and that gives us a fermionic and a bosonic Hamiltonian, of which we know that they're quadratic and have the same spectrum. So for the fermionic part, this, will look like this. Yeah. So it becomes a fermionic, hopping Hamiltonian, where we, hop, from, let's say, a sublattice B to a sublattice A. Yeah? And there's some matrix in between, that tells us, how we hop between these two sublattices. And for the bosons, we see that, the Hamiltonian becomes this form. Yeah. So first of all, we see that there's only one type of site involved here. Yeah? So we have, a distinction now, when we talk about lattice geometries of, where the bosonic operators live and where the fermionic operators live. So the fermionic operators, live on sublattices A and B. The bosonic ones, consistently live on just, one of the two sublattices. In this example, they live on sublattice B. Yeah, and both of them, Q and P, live on that sublattice. And then if you look at this bosonic Hamiltonian, we see that, this A transpose A, that's the dynamical matrix, of the mechanical system. And this pi, is p squared. So the identity in front of this is the mass term, which you have set to unity here. Okay. So in combination, R is simply the rigidity matrix, of the mechanical system, written in these bosonic operators. Yeah. So what we see is, what we connect here now is, this idea of, a mechanical system, real bosons connected to real fermions and Majorana story. Yeah, and vice versa. Yeah, so we can either say, well, we have a mechanical system and we map it to some Majorana Hamiltonian, or we have some Majorana Hamiltonian and say, well, we can construct a mechanical system for that. Yeah. There's one more step that we actually have to do, and that is, so far everything is quantum mechanical. Yeah. So both, the fermionic operators are Majorana fermion operators, and also the bosonic operators are quantum. Yeah. But the mechanical system that we build, this Lego thing, or balls and springs, that's a 100% classical system. So we have to take a classical limit. Yeah. So the next step is that on the bosonic side we go from quantum to classical. Yeah. So we go from those real bosons to classical balls and springs. Yeah. And write that down. So we go to the classical limit and basically make these classical operators. And now we really write, down something in terms of balls and springs, so where there's, a kinetic term. And then there is, in the real space coordinates, there's all kinds of, spring constants. Yeah. And the spring constants that we have are intersite spring constants. So that's, those guys here, yeah, that, go between sides. And then there's a spring constant also on the side that, need to be defined. And, here's how they're, relate, to this, dynamical matrix A that we have defined here. Yeah. So this is how this entire system looks like. Yeah, he takes the classical limit of the quantum bosonic model. Okay, so now we have a recipe of how we can go from a Majorana fermion Hamiltonian to a classical balls and spring model. And let's actually do this. Yeah? And let's play and let's look at one of these Majorana fermion Hamiltonians that we like. And well, which one do we like? Why not do this on a spin model, which you can write in terms of Majorana fermions and that you all know. So let's look at the Kitaev honeycomb model and its mechanical analog. Okay, so we start with a spin model that lives on a honeycomb lattice and is about bond directional interactions, where you have these Ising-like interactions along the three principal type of bonds in the lattice, and you couple as x, as y, or as z, and you go in the x, y, z direction, and we have learned that we can solve this model analytically exact by recasting it, for instance, in Majorana fermions. That's how Alexei Kitaev did this. And the trick is that you decompose into Majorana fermions and then recompose some of the Majorana fermions into a gauge field, a Z2 gauge field, and end up at the end of the day with a free Majorana fermion Hamiltonian in the background of that static gauge field that you can then solve exactly. And the solution of this model is a function of the coupling parameters. Yeah, so if they're all the same size, you get a gapless spin liquid with a Dirac spectrum, which we immediately understand. We have a honeycomb lattice on which free fermions form this Dirac structure. If you vary these couplings, these Dirac cones start to move around in momentum space. Eventually, they will merge and you gap out into a gap spin liquid state. If one of the three couplings is bigger than the other two. So that's the super well-known phase diagram of that model. And at the end of the day, it's a Majorana fermion Hamiltonian. So this spin Hamiltonian, can be written as a free Majorana fermion Hamiltonian. And now we will translate that free Majorana fermion Hamiltonian, using the recipe from above into a pulse and spring model. So we go from this honeycomb model, where the Majorana fermions live on the two sides of the honeycomb lattice to the corresponding balls and string model. So now remember when I said when we do this mapping, the bosonic degrees of freedom only live on one of the two sublattices. So that actually means that the model that we will look at will be defined only on one of the two sublattices of the honeycomb lattice, and that is a triangular lattice. So we define a triangular lattice, balls and string model. And then we go through our recipe as well, and we look at these, these spring constants. We get numbers for them, and at some point, we should mention that they have different signs. These two spring constants, which at the end of the day is not really a problem. And then we have this model which looks like this. So it's a triangular lattice, balls and string models where there is interside springs and on-side springs. Okay, so in principle, we now already know what we should have. By this, supersymmetric construction, the classical model that we have written down here, has to have a spectrum that we know from the spin liquid. But let's actually find out. And the way that we played with this, more specifically, how Jan, my student, played with this, is that you can take just a very large instance of this balls and spring models, with 40 times 40 balls and springs. Generate this large lattice, and then solve the differential equations that describe that classical mechanical system when you start shaking it. So we take like the middle side and we start shaking it with different frequencies, and we probe energy modes at different energies this way. We shake it slowly or very fastly. Let me show you the numerical simulation that comes out of this. Okay, so this is the model that we look at. We will oscillate the middle side, which will sit here, and then we will look what happens. And this is what happens. You shake, and so your balls and springs will actually connect to this, and this pattern that forms in real space we can Fourier transform. Okay, so that's here on the left. Down here, that's a Fourier transform to every single configuration that you see here, and the above plot is one that is time average, and then you see some spectrum. Okay, so in Fourier space. Okay, so let's do this many times. And for different frequencies, which we oscillate our system, and record these spectra from this. Put everything on top of one another. So take these spectra, which correspond to different driving frequencies in momentum space, and that way, we get an entire spectrum. And here it is. So this way you can, take the classical model and then, learn something about the classical model and its entire, energy spectrum. And then you will find this dispersion, which, if you have a trained eye, you would say, well, this dispersion, I've seen many times in my life. At the K point in momentum space, there is a Dirac cone-like structure with a linear dispersion going both ways. And yep, here at the endpoint there's that line, and here's the top of the spectrum. So that's a electronic dispersion from graphene, now seen in this string model. You say, well, this is what you should have gotten because you did this supersymmetric operation, and as such, this should have come out, and yes, it did. And it's fun to see that it came out. If you think about the classical system, you might actually come to the conclusion that it's not totally trivial what you're seeing here. Every classical spring that you're looking at has a quadratic energy dispersion. So the fact that your this matrix of many balls and springs has collectively a linear dispersion coming out of zero energy, zero frequency. is truly a collective phenomenon. Yeah. So many quadratic dispersions make a linear Dirac cone for all of them. Yeah. So you might say, oh, that is not unexpected. You might have a Goldstone mode. The system is, well, yeah, but no. Yeah. So this system doesn't have a Goldstone mode. Yeah, because we have broken symmetry explicitly. That is in the very beginning. Yeah. So so no Goldstone modes here. And this becomes even more visible when you go to the gapped phase from the Guitar model. So when you make one of these couplings larger than the others, yeah. So if you do that, then the dispersion that your classical system will show, it will have a gap. Yeah. So there's no gapless mode. Yeah. Actually, there's no low frequency mode at all. Yeah. So the system is actually rigid. Yeah. At low frequencies. Yeah. So when you try to excite it with a low frequency, the system doesn't respond. Yeah, that's actually very unusual. Yeah, so it only responds, at a certain threshold. All of a sudden, it's like, oh yeah. So now I start to resonate and wiggle. Well, for all frequency below that, it's not reacting at all. So it's very rigid, which is again a very unusual situation for a mechanical system. Yeah, so we have if you will, we have designed mechanical systems that have interesting properties, yeah, where we can tune, for instance, this low versus high frequency rigidity, very much to the point, because we know how to construct these type of band structures in electronic systems, because we have so much experience doing that, of course. Now, in recent years, we have educated us collectively about free fermion band structures like crazy, and not only Dirac spectra, but topological insulator spectra and higher order topological insulator spectra. So let's do that. Yeah. So let's try to design such a mechanical higher order topological insulator. Yeah. And we will start again from an interesting different location. Our mapping, if you want to end up with a mechanical system, we have to start with a Majorana fermion system. Yeah. So we want to start with a quantum spin liquid, that has Majorana corner modes. Okay. Ooh, yeah. So where do you get that? Well, you go to a more generalized K-type model. Yeah. So if you go to a lattice structure like this, yeah. So it's called the Sutherland lattice, because there's a dimer model that Justin Sutherland looked at, and this lattice that is nicely soluble, and has some relation to this compound, which here is not relevant. We're just taking that lattice geometry, and we put again a K-type model on it. Yeah. So what's so special about this lattice geometry from that perspective? Well, it's 5 coordinated, so it has an odd coordination number, and that is actually key to writing down an exactly solvable K-type model. Yeah. So if you have a spin that folds apart into 6 Majorana fermions, then you can again solve that exactly. So that actually means that the original spin model that you would like to write down is a spin 3/2 gamma matrix type spin model. So we have actually done this. Yeah. So together with Watzwald, Vidi, and Kieran Hickey, and my other graduate student Timeshman, we have formulated this model, we solved it, and by staggering between these plaquettes, you can actually achieve the feat of having different types of Majorana band structures. Yeah, so you can have a trivial band insulating band structure, and in that sense you then get a trivial spin liquid, but you can also get a churn insulator. So a churn insulator is like a topological insulator. So it's a band structure which has some non-trivial barrier curvature, and as such gives rise to a chiral edge mode on the boundary. Yeah. In terms of spin liquids, that means that you have a model that realizes what's called a chiral spin liquid. Yeah. So that's also nice. And then funnily, you can also get the next level. Yeah. So between trivial, a one-dimensional corner mode, you can also generate something where you get localized corner modes. Yeah. So where you have in each corner of the system, you have a gapless mode, a free dangling Majorana. So that is the incarnation of a second order topological insulator, and we call that parent state, of which it is a second order spin liquid. Anyway, so So again, we have, a system, which has an interesting Majorana band structure, and now we do the translation, and in doing the translation, we note that, this lattice structure is, it's just a deformed way of a square lattice. So the model can also be written down like this in a square type form, and then you end up, because the sublattice of the square lattice is also a square lattice, you end up with a model of bolts and strings also on the square lattice, and that square lattice model, you can by tuning the strengths of couplings, these squares, you can go as a function of this parameter between two gapped phases. There's a gapless point in between, and one of the two gapped phases is trivial, and the other one has a topological invariant. It's this higher order topological insulator. And for two of these points, so one here exactly at the gapless point, and one further out. Here we see the spectra of the mechanical system. Where Jan did exactly the same thing. He started to wiggle some frequency, Fourier transform the real space system, and then show that the mechanical system has exactly the spectrum that from the fermion Hamiltonian. And this is the most complicated way of arguing that this should be existing. The phonon insulator has actually been observed. Again, Sebastian Huber's group was very influential in doing this and showing us, that this higher order topological insulator state can also be built in a mechanical system. So what's the benefit of what we have done? This is supersymmetric connection. One benefit might be that you can construct these models, but on a deeper conceptual level, it's actually a story about topological invariants that you can define. So why is that interesting? Well, it's interesting because we can now go in and we can define topological invariants for the bosonic system. We are probably very used to the idea of topological invariants for fermionic systems. So that works like this. So you have some fermionic eigenstate of some Hamiltonian, and you can define a Berry curvature in this way. And this fermionic Berry curvature then allows you to calculate things like a Chern number if you integrate over momentum space for a band, or other invariants that are for instance relevant to these higher order topological insulators. Now, if I'm in a position to define a topological invariant for a fermionic system, the supersymmetric connection allows me to do something for the bosonic system as well. And how does it work? Well, I take the fermionic system and I map it to the bosonic one, using the supersymmetric trick, which we saw, the supersymmetry operator, all it encoded was this rigidity matrix. So me as a rigidity matrix, I can take the fermionic state, so the fermionic eigenstate, and go over to the bosonic eigenstate, or vice versa. So I can connect the fermionic to the bosonic, or the bosonic to the fermionic. In particular, if I have a bosonic state, we are using the rigidity matrix, I can end up with its corresponding supersymmetric fermionic partner. But that actually allows me to define a Berry curvature for the bosonic system. So a supersymmetric Berry curvature, where I start with the bosonic system, I take the eigenstate of the bosonic system, translate it to fermions, then calculate a Berry curvature, and then translate everything back to the bosons. And so this bottom line here is what you actually get. So you see that the bosonic Berry curvature defines this way is actually different from the fermionic one written up here, in that it has this additional covariant derivative, which comes from the SUSY operation that you're performing. So you're actually defining something more general than the conventional bosonic Berry curvature in this example by using the SUSY connection. So the conventional Berry curvature is trivial for most bosonic systems. So bosonic systems are very boring most of the time. And very different from their fermionic counterparts, which are very rich and which have been classified, where we know a lot about what kind of topological states we can have by for instance this tenfold weight classification. Now, bosonic systems looked super boring from that perspective, and now it turns out that if you define this more complicated Berry curvature. So it's sort of a Berry curvature of a Berry curvature. Yeah. Then you can, imprint, this topological idea also on bosonic systems, that initially look very boring. So, for instance, seeing that, this higher order TI actually plays out in that bosonic system, requires you to look at something like this to actually see it, yeah, and do this. Yeah. Good. Okay, so for the bosonic system, I can define this, Berry curvature. Let me give you an example. For exactly this higher order TI, you can actually go in and Krishanu has done this, beautiful calculation of, then defining a Wilson loop operator, boundary Hamiltonian, and calculate the bosonic Berry curvature, which tells you exactly that these two phases, in the mechanical system are distinct. Yeah, so they come out, this Berry curvature 0, trivial, or 1, being non-trivial. Yeah, and it's something that you can actually see this way, very sharply, exactly in the same way that we are trained to see this in fermionic systems. So I actually think that is a nice result that might be helpful in further classifying topological properties of bosonic systems by going through this supersymmetric story. Now let me switch gears and tell you a second story, which initially looks very different. Yeah, it's about spin spirals, and hang in with me for a few minutes, and you will see. We will come back, to the supersymmetric story that we just heard. From a very different perspective. Yeah. So what's a spin spiral? Well, something like this. Yeah. So you go through space, and there is some spin, rotating. So that's a coplanar spin spiral. Yeah. So we have a plane in which this spin can rotate, and as you go through space, you rotate in that plane. You might write it down like this, and the most important thing in writing it down like this is that there's some momentum q that defines how quickly that spin spiral rotates as you go in space. Yeah. So these types of spin spirals you find in all kinds of situations. Multiferroics. The ingredient that allows them to be that is that there is a spin spiral. Spin textures, multi-Q states, and spiral spin liquids. That's what we discuss here. All live from this idea that there is some magnetic system that has a spin spiral built in. Yeah? So the simplest story about a spin spiral is probably this. Yeah? So the 120-degree order in the triangle lattice antiferromagnet. Yeah? So you take an antiferromagnet of O3 Heisenberg spins, can be classical. You put it on a triangular lattice, and you will get this 3 sublattice order. Where around a plaquette, where these 3 sublattices meet. You rotate your spins by 120 degrees. Yeah? There's 2 ways of doing this. They can all point in or they can all point out. Yeah. And these different rotations. Now if you look at this direction here, they you see that the spins actually form this spin spiral. There's 2 q vectors. For that, it's these 2. Yeah, plus or minus 2 pi over 3, 2 pi over square root of 3. Yeah. So the k points in momentum space. Okay. Good. So 120-degree order, yeah, this is the simplest spin spiral you might have in mind. Let's go to 3 dimensions and look at the richer family of spin spirals in a family of antiferromagnets, that we define in the diamond lattice. So the diamond lattice, it's a bipartite lattice, so it's actually not prone to form particularly interesting antiferromagnetic states. Well, only if you actually induce a next nearest neighbor coupling, that will actually happen. So if you put this J2 and you couple only one sublattice, which is an FCC sublattice in the diamond lattice, interesting things happen. And there's a number of materials, so-called A-side spinels, where the A side, so it's the first side here, it's A, B, and sulfur or oxygen here. The A side, carries magnetism, that realize, such magnetism with spins of different lengths. Yeah, so manganese strontium sulfide, this 5 half spins is it's a good classical system. Yeah, good. So so you can look at the the spin spirals that form in such A-side spinels by describing them by this very simple J1, J2 Heisenberg model on the diamond lattice. And what you will find is that there is actually a degeneracy of spin spirals. Yeah. So when you look, for instance, at this value, that J2 is 0.2 of J1, you will find that there is not two spin spirals like in the 120-degree order that we just described, but there's many different Q vectors that are allowed, and there's a sub-extensive degeneracy in the ground state described by these spin spirals of different Q vectors. And if you take the manifold of Q vectors and plot them, they look like this. Yeah, so it's this bubble here, and then as you vary this relative coupling strength, this manifold of allowed Q vectors for these spin spirals, that varies. Yeah, so it looks like this, and then in the limit of going to the FCC lattice, you get these lines in momentum space. Okay, so that it's actually stuff that I did a long time ago while in Santa Barbara together with Leon and Doran Beckman and Jason Alishia, Emmanuel Goul. We wrote a very nice paper in 2007 that these things must exist, these spin spirals. It took 10 years, and Christian Rüeg's group at PSI to actually do the neutron scattering experiment on manganese constant feed to actually see these spin spirals in the real material. Yeah, so if you do manganese constant feed, nice crystals, cool them down, you do your neutron scattering, you see these cuts. The cut is here, through this surface, the spin spiral surface, and they have been seen in experiments. These guys at PSI have done follow-up experiments in the last year where they have taken these spin spirals to the next level and then looked at fermions and really nice stuff coming out of this. Okay, so that's actually real. These spin spirals. But here, we want to actually take a different perspective and again look at these spiral manifolds. Yeah. So I've said that
I have a little question in a past slide.
Oh, absolutely. Yeah.
So this is a commensurate spiral, right?
No.
No.
So
okay.
so the this manifold, it's really so all of these they can be anywhere in the Brillouin zone. Yeah.
Mm-hmm.
And it's an entire manifold, as you see. So some of them, if you take particular asymmetry points, they're nice commensurate spirals, but generically they're not.
Okay.
Which technically is a pain if you want to do numerics, but for the real system, it doesn't matter.
Okay. Thank you.
Yeah. Okay, so we have these different manifolds. Yeah. So let me again say, for this diamond lattice, so every point on the this I don't know what color that actually is, this shaded manifold is an allowed Q vector. So there's many of them. Yeah. You have a three-dimensional system, and this manifold is two-dimensional. Yeah. So that's the diamond lattice. I also showed you the result for the FCC lattice. Yeah. So if you go to the extreme case where there's only one sublattice, that's the FCC, the phase centered cubic lattice. Where you have these lines here. Yeah. And then the triangular lattice, we initially had these two 120-degree orders. Now, if I would show you this picture and say, look here are Brillouin zones and here are points of interest, yeah, you would say, well, yeah, what you're showing to me are Fermi surfaces. That's a Fermi surface, that's a nodal line, that's a Dirac. Yeah, so so these manifolds, they can have different dimensionality, and we know everything about those. Yeah, so this connection we now want to make, between the spiral manifold in this classical spin system and the Fermi surface in the fermionic system. And now you see that this will end up with some supersymmetry story again. But before we get there, let's go through this. Yeah, oops. So we want to connect these different manifolds. Yeah, but they're actually coming from very different worlds. Yeah, so one is the ground state manifold of a classical spin system. The other, the Fermi surface is a mid-spectrum state of a fermionic quantum system. So how can we actually connect these two? Yeah. Well, let's go through something very elementary to see how, and see how we actually can connect this. So let's actually see how we calculate, these spin spirals. So how do we actually get these manifolds? Yeah. So we start with some, spin Hamiltonian, classical spin Hamiltonian. These are all three spins, some interactions. And what we do is, we Fourier transform that, spin model, get an interaction matrix in K-space, which we diagonalize and then look for its minimal eigenvalues. Okay, so that's it's called Lattice. Okay, you better check that all your eigenvalues still conserve spin lengths, and that your spins are not fluctuating. But that's a minor detail here. Yeah. So you say, well, that's of course not very different from what we do when we calculate something for free fermions. In particular, if you look at the Fermi surface, we write down the hopping Hamiltonian, free fermion Hamiltonian. Go to Fourier space, diagonalize in Fourier space, find zero eigenvalues. That's what the Fermi surface is in a system that has particle symmetry. Yeah. Aha. So the spin spirals, are the minimal eigenvalues of the spin interaction matrix M. Yeah, and the Fermi surface is this mid spectrum, so the zero eigenvalue states of that fermionic Hamiltonian. So these two we now want to bring in correspondence. So now on the one hand side we have the state on the bottom of the spectrum, and the other we have the state in the middle of the spectrum. So how do we make those identical? It's a very simple trick. We take the spectrum where we want to select those zero energy states. We square it. Yeah. So if we square that Hamiltonian, everything negative will become positive. Yeah. And what's zero remains zero. So by squaring the fermionic Hamiltonian, the manifold of zero eigenvalue states becomes the manifold of minimal eigenvalue states. Oh, and that's so now we have a correspondence that we can make. Yeah. So what we want to identify is the square of the fermionic matrix. This is magnetic interaction matrix. And so this so here these guys come out now as zero energy states. The ground state of the magnetic system might have some grounded energy, so that there's some offset trivial which we subtract here to make a zero. Okay, so this is how this connection works. Yeah, so we go from the spin system to the fermionic system, and from the fermionic system to the spin system. So we just said from fermions to spin we have to square the Hamiltonian. Yeah, it means in reverse, going from the spin system to the fermions, we have to take a square root. Aha. Taking the square root, in a matrix correspondence, well, that is with what I started my talk. So when I talked about topological mechanics, I said, well, there's a one-to-one matrix correspondence, which involves taking a square root. Yeah. So what we're discussing here is actually very reminiscent of that topological mechanics story. Yeah. So let's look at this in more detail. Yeah. And try to understand what squaring of the quantum system means here. Yeah? So that's the perspective we want to take, and what we want to evolve in doing that is an explicit lattice construction. Yeah. So we want to connect lattices with one another. Okay. Okay. So here it goes. Yeah. So if I have some fermionic Hamiltonian with some lattice. So let's say I have free fermions with honeycomb lattice, and I square my Hamiltonian. Yeah. So that actually means that out of every hopping, I would like to make hopping squared. Yeah. But hopping squared is actually decoupling the sublattices. Yeah. Because twice hopping. Yeah. You go from from one sublattice to the other, but you actually remain on the sublattice. Yeah. So by squaring your Hamiltonian, what you effectively do is that you talk about the two distinct sublattices of your bipartite lattice here. And now we actually see the correspondence again. Yeah. And now it cries out to us. Yeah. So I said at some point the 120-degree order of the triangle that is antiferromagnet is this K point. Yeah. In momentum space, and that's of course also what we immediately associate with the honeycomb lattice. So free fermions on the honeycomb lattice have direct point at the K point and the K prime point. Yeah, which have exactly the momenta, K and K prime, which correspond to these two Q states of the spin spiral order. Aha. So this is what we are connecting. Yeah. So the 120-degree spin spiral order is the partner of the direct points on the honeycomb lattice. And now you see the lattice correspondence. Yeah. Triangle lattice here, honeycomb lattice here. Yeah. And you can play this game with all of these structures that I showed you. Yeah? So for instance, if you talk about the FCC spin spirals, which form these lines momentum space, those correspond to the nodal lines of free fermions on the diamond lattice. Yeah. So if you were for some reason interested in free fermions on the diamond lattice, you would know this spectrum also by heart. That there is these nodal lines forming here in the squares of the Sabellino zones. Okay, so so let's be more explicit how we actually do this, lattice going back and forth, yeah, and let me show you how how one does it, yeah. So red means always now spin Hamiltonian, blue means fermionic Hamiltonian, and we go between, yeah. So when we go from the spin Hamiltonian to the fermionic Hamiltonian, we have to take a square root, yeah. And here's how a square root in lattices looks like, yeah. So for instance, if you have a fully connected plaquette, like this square, yeah, where you connect also the diagonals, yeah, that will be made into this, yeah. So you generate a 4-coordinated side in the middle of this structure. Likewise, in the triangle, which is the fully connected plaquette of 3 spins or 3 sides, yeah, you would construct something like this, yeah. So again, the fourth, the 3 sides plus an interstitial side, and the bond between 2 sides, which is a fully connected version of 2 guys being connected, you insert an additional side. Yeah, so that's a complicated direction of taking square roots. Squaring things, so going back, from the fermions to the magnetic Hamiltonian, that involved, a squaring. You see that is then just, the sublattice construction. Yeah, so you go here and you decouple, the 2 sublattices, the blue and the white ones here in the intermediate. Was there a question? If not, let me now actually, now that we know how to do, this lattice correspondence, and just flash you 1 or 2 examples that go beyond what we just said in how spectra correspond to one another. For instance, yeah, if you're interested in spins on the Kagame lattice, classical spins on the Kagame lattice, yeah, this lattice construction will tell you, well, if you want to go from the lattice of these corner sharing triangles to a lattice of fermions, you have to take a square root of this triangle, which means putting that interstitial side in, and you end up with this lattice structure, which is this decorated honeycomb lattice, where the gray dots they form a honeycomb, and these white dots they're on the bonds between them. You actually see the white dots here are exactly the same white dots as up here, yeah? So there's still the Kagame here. And so these guys are isospectral up to this business of square rooting and taking squares. So you see that these 2 spectra, they're actually identical, yeah, but squares, yeah. So if you go from the fermions to the spins, you take actually this dispersion and you just square it, yeah. So what was linear here, yeah, comes now the Magnon mode in the spin Hamiltonian, yeah. But this spectrum has positive and negative part, and the Fermi surface, which is mutually degenerate. This is flat band, becomes this in the classical version, yeah. With these Magnon bands, or the other way around, as you like it. Let's go to 3 dimensions. Show another example. Yeah, if the spins live on the Pyrochlore lattice, yeah, then the corresponding fermionic version, yeah, is a decorated honeycomb, decorated diamond lattice, yeah. So it's diamond lattice, so side in the middle of it bond, yeah, and you can see these 2 spectra are identical. If you take the square root of this one, or if you square that one, you can go back and forth between the 2. Yeah. So that's how you can connect these spectra, how you can connect the language of a fully degenerate, extensively degenerate manifold of states in the Pyrochlore antiferromagnet to a fermionic spectrum with a flat band, at the Fermi surface. So now let's we said we wanted to do this all now in supersymmetry. So how does it actually be formulated in supersymmetry? Yeah, here it is. So we have said that our lattice construction, is about sublattices, yeah. And actually the 2 sublattices, those are the supersymmetric partners, yeah. And the combined lattice, where the 2 lattices are formed into one. So for instance, here the honeycomb and this Kagame, they form this decorated honeycomb. That's a SUSY charge. So these are supersymmetric partners, and that's a SUSY charge. Yeah. So going from one of these guys over here is taking the square root, or going the other way is squared. And you see that, yeah. So again, linear becomes quadratic, and all the features of the spectrum are reproduced. And the real supersymmetric partners, yeah, are these 2 guys. Yeah. So I call one boson and one fermion. Now, the other way around. Yeah. So these 2 lattices must have isospectral energy spectra. Yeah, and they do. Yeah. So you look at these, and you say, well, they're identical up to a flat band here. Yeah? So there's a flat band. There's a zero energy mode. Yeah, that's actually exactly what is allowed. Going the supersymmetry. The supersymmetry allows you to map spectra upon one another up to the zero energy modes. Yeah. So this flat band has a connection to the Witten index, and actually comes from the fact that these two sublattices have different number of sites in the unit cell. Yeah. So honeycomb has 2. This guy has 3. They're isospectral, meaning the Kagome must have a zero energy mode. Yeah, because well, there's only 2 dispersing modes in the honeycomb, which must be isospectral to the Kagome lattice, and then the third band, which you have to have because you have 3 sites in the unit cell, that has to be a zero energy mode. Yeah, so it's a flat band. Yeah, so it's actually a very easy exercise now to construct models. So if you're in the business of studying a system with flat bands, if you're interested in interesting models, that can mimic twisted bilayer graphene with flat bands. So here, take the Kagome that has a flat band, by geometry built in right from the beginning. Yeah. Good. In my last minute, I will give you another example of a supersymmetry connection between 2 quantum spin liquids. And it's actually this connection which started this project with the Cornell. So my student Jan and I, we had worked out this correspondence between spin spirals and fermions, and I was at at a summer school in Cornell, and I was lecturing, and I told this story to Michael Lawler, and he was like, I think I know this story from a totally different context, and that's when we started to understand this supersymmetric connection. And one of the first principal examples that we connected was actually a totally different one. Yeah, and here it is. Yeah, so there's a lattice geometry called Hyperkarma lattice. Yeah, so that's a Kagome in 3 dimensions. Yeah, so it's corner sharing triangles in 3 dimensions, and there's sodium iridate. Yeah, sodium 4, iridium 3, oxygen 8. In the last 15 years or so, initially synthesized by Takagi, is one of the first J1/2 mod insulators. That shows interesting physics. It's a very good spin 1/2 spin liquid candidate in 3 dimensions up to this day. And right after this the synthesis of this material, people started to think, what is it actually? What kind of spin liquid? And there was a nice paper by Michael Lawler, Arun, Youngberg, and Leon. Where they talk, well, this must be a gapless quantum spin liquid with a spin on Fermi surface. Yeah. Okay. So what that mean? Yeah. So it means it's a spin liquid where the spin degrees of freedom decompose. They're fractionalized into complex fermions and the U1 gauge field. And the complex fermions, those are spinons, and they form a Fermi surface, a spin on Fermi surface. So there's a gapless manifold of these spinons. Specific heat of such a system would go like T log 1/T, and this paper discussed it at length. Why you don't see this log 1/T in this data here in the experiment. Okay, so that's one story, and it seems very disconnected from another story that Maria Hermans and I entertained ourselves with, and that was looking at 3-dimensional generalizations of the Kitaev model. So you go to lattices in 3 dimensions that are also tricoordinate, just like the honeycomb lattice in 2 dimensions. And one of these lattice geometries that we looked at was the so-called hyperoctagon. Well, don't ask me why it's called that way. We came up with that name because hyper honeycomb was already taken, and there's this octagon shape here. Yeah. Okay. Now, long story short, if you diagonalize your Majorana fermion Hamiltonian after fractionalization of that spin model, yeah, what you will find is a Majorana Fermi surface. Yeah. So we said, this is a cool model. Yeah, this 3-dimensional Kitaev model. It has a Majorana Fermi surface. Yeah, that's as spin liquidy as it can get, because if you look at the specific heat, it's linear in temperature. Yeah, so it really looks like a metal. Yeah, and that's really what a spin liquid is. Yeah? So and it's slightly obscure because its Fermi surface is made of Majorana fermions, so these spinless partons, that coupled to a Z2 gauge field in this Kitaev construction. So this story looks very different from what I just told you. Yeah. So these 2 lattices, yeah, they're both discussed as examples of gapless spin liquids. Yeah. And most of the time when people do this, the first thing that they have in mind when discussing the difference is actually the gauge structure. Yeah. So the Kitaev one has a Z2 gauge structure. Here's a spin on Fermi surface story as a U1 gauge structure. And that manifests itself in very different specific heat evolutions. But here I'm more interested in the fact that we have spin-on Fermi surfaces and Majorana Fermi surfaces, and actually it turns out that these things are exactly the same story. Yeah. So why is that? You can go back and forth between these two lattices. These are almost the same lattices. They are medial and pre-medial lattices of one another. You can actually see this, in the way that these photographs, are taken. So I just said, the hyperoctagon has this octagon here. Yeah? So it's a particular shape, and there's these squares. And if you look, more closely, you will see that the squares, actually, spirals, winding one way, and the octagons wind the other way. And now, if you have a lot of imagination, you will see the same features in this, hyperkagami lattice. Here's the octagon. These elongated things are octagons, and then there's little squares here. Yeah. And around these squares and octagons, there's triangles, forming spirals, that go this way or that way. Yeah. An easier way to see that these are almost the same lattices is, saying what actually medial and pre-medial means. Yeah. It means, that you take a triangle here, yeah, and you make it into a single dot here, yeah, in a tri-coordinated side. Yeah. So every triangle, from the hyperkagami, you identify as a tri-coordinated side. And then, because the triangles in the hyperkagami are corner sharing, yeah. So every triangle has three other triangles around it. Now you will end up with a tri-coordinated lattice when you do this replacement. Yeah. So you will go from the hyperkagami to the what we call hyperoctagon. Yeah. And now this step here, of taking one fully connected plaquette and replacing it with this interstitial side, that is exactly what you heard about in this lattice construction, the supersymmetric construction that we use to display explain this spin spiral surface versus fermion surface story in the last section. So we can apply this here too, and we will immediately find that these spectra of these two lattices isospectral, so they have the same spectrum. So here is a band structure that Michael had calculated for the hyperkagami. Yeah, and where you take some cut and you discuss how along that cut you get that that spin-on Fermi surface. So now you might look at these other spectrum here and say, well, it doesn't look like it. Huh? It looks different. Well, yes, it looks different because we got away with taking a smaller unit cell in this hyperoctagon. But if we double the unit cell, yeah, so we can double the spectrum and fold it back. Yeah. So if we then do this, we just I don't know whether we are lazy or we're not lazy, but we are taking a bigger unit cell to describe the same lattice. Then you actually see, whoops, you get exactly the same spectrum. In discussing the Majorana Fermi surface, we were taking the cut at a slightly different location, through the spectrum. That's because of particle hole symmetry and other features. But in principle, these two stories are deeply related, again by the supersymmetry story. Yeah. Okay, so let me close here. Time is up. There's a summary. We discussed connections, interesting connections using supersymmetry. The first one was to do topological mechanics for supersymmetry and going to the level not of saying there's a supersymmetric matrix involved, but going to the degrees of freedom and making a supersymmetric connection between the degrees of freedom, so that we could describe a fermionic and a bosonic Hamiltonian. The bosonic one, we could take the classical limit of and make it a mechanical system, and the fermionic one we saw was naturally a Majorana fermion system. Yeah. What that connection allowed us to do was to define a topological invariant for bosonic systems. That is defining a Berry curvature in a new way. This which it's an extension of the conventional Berry curvature, and which allows us for bosonic systems to identify interesting topological states where the conventional Berry curvature would be meaningless. And then we have seen many other supersymmetric pairs of states, spin spirals and fermions. So how magnetism and Fermi liquids are connected to one another. And in the last example, I showed you a cool example of connecting to quantum splits. Yeah, is one another. And now, because you have made it to the end of the talk, you have the benefit of watching me playing with my soap liquid last weekend here at minus 10 degrees Celsius on my balcony, and you see how it freezes over. And with that video, I stop and I look forward to your questions.
Okay, so now the floor is open. If you have any questions, you can either raise your virtual hand or you could just unmute and ask it if you like.
So if I can, yeah. So I find it very interesting that because of this supersymmetry constraints that we actually can get non-trivial bosonic Berry curvature in this case. So I'm wondering, because we do have let's say bosonic topological states that like bosonic topological insulators or bosonic quantum Hall systems, but in that case, I think interactions are very crucial, because if there are no interactions, then the system is basically trivial. So I'm wondering, in your case, what if we actually consider interactions?
Yeah. So so the statement is actually simpler. Yeah. So that's absolutely right. So I've been talking about non-interacting systems all the time here. Yeah. So both the fermionic and the bosonic ones are non-interacting, and it's indeed an interesting question how you can go from the single particle picture to a many particle picture and try to get the entire SUSY construction through that. Yeah. So it's not so much about the effect of interactions, but describing true quantum many-body states, ground states, also in the supersymmetric pair. Yeah, that's yes, that's true. That's one of the things we would like to do in doing this further. At this point, what's remarkable is that even for the non-interacting bosonic system, yeah. I can now provide you with an insight, whether there is some deeper topology hidden in the system or not. Yeah, which is which is interesting, because you don't have to treat interaction. Yeah, so that's the point here. Yeah, so you can get a topological state in bosonic system even without interactions. Yeah, but you have to look at the right thing to see it. Yeah, so you have to look at this higher order Berry curvature.
Mm-hmm. See. Thanks.
So any other questions? So I have a question. For the Majorana Fermi surface, you said that the specific heat basically goes linear with T. So basically there's a Sommerfeld coefficient. How does the next leading order term go?
Oh, that I don't know. But it's so in that case, it's actually simple, because it's really, I would think it's just like Fermi liquid theory. So, so in principle, in that case, where we talk about these Majorana Fermi, fermion spin liquids, the finite temperature behavior is again, like in Fermi liquid theory, defined by the codimension of your manifold. Yeah, meaning that if you have a surface like the one that I showed you, you get a linear specific heat. Yeah, but if you get a nodal line in 3 dimensions, it's quadratic, and if you have a Dirac or Weil, we also have Weil spin liquids where you have just Weil nodes. Then you have a cubic specific heat. So in that case, it actually works. The U1 spin liquid was different in its specific heat because of the gauge structure. Yeah, so you have this heavily fluctuating gauge field, which at very low temperatures, you will actually see as a contribution in the specific heat. Now, what's actually more interesting, and because it deviates, is the story for the spiral spin liquid. While we have made this connection at 0 temperature, connecting the the spin spiral ground state, to the Fermi surface. That's 0 temperature physics, and that works. But as you actually go and look at finite temperatures, you will find that these systems are actually different. Yeah. So, well, for the Fermi system, it's still the codimension that counts. For the spin system, it's actually it's a different story. Yeah. So because there you actually realize all of a sudden that your spin degrees can fluctuate easily along the spin spiral surface, and they cannot orthogonally. And when you do the calculation, you will find that there is more general exponents for the specific heat. For instance, if you look at this spin spiral surface in 3 dimensions, it does not go linear in temperature, but it goes to T to the 1/3. Yeah, so it's slightly non-trivial. So the finite temperature physics is actually different. So Gang Chen actually recently wrote a paper, elucidating this on a number of other examples as well. That the finite temperature physics is different. Yeah. So that it comes from this fluctuation story. In technical terms, where does this correspondence break down? It breaks down on the level of the Lagrange-Hitza calculation. Yeah, so you cannot do Lagrange-Hitza for finite temperature states. Yeah? But that's what was built in here for the zero temperature calculation that actually works. Yeah, and then you have a strict correspondence, but at finite temperature it doesn't work. Yeah.
Okay, so building off that question, then, in like a normal Fermi liquid, sometimes you get non-analyticities in specific heat due to quasi-particle quasi-whole scattering. So would you expect to get some kind of non-analyticity due to some similar effect in the spin-on or Majorana Fermi surface in these systems?
Yeah. I don't know. So here you have to now carefully, think about symmetry classes. Yeah. So you're in this particle hole symmetry class. So you're always in symmetry class BD1 in this, free fermion categorization. Yeah. So that's actually the system that you have. Yeah. And then you have to ask, which processes are still allowed or not. Yeah. Let me say, what this question about finite temperature might be an interesting one. Yeah. But it's one that is not necessarily, as I just said, captured by this back and forth. But what is actually captured is everything that is at zero temperature. So if you're actually asking about disorder effects at zero temperature, on these manifolds, yeah, and let's say you are super educated about graphene, yeah, because well, that's an interesting problem, disorder in graphene, yeah. So everything about a disorder in these systems, by this translation, now everything I think about disorder in the 120-degree magnetic order. If that's relevant for you, then you can just translate everything back and forth, yeah, because that's strictly zero temperature physics, and it should work, yeah. And I think that's a benefit. Yeah? So so vacancy in the dive model, yeah, you can translate back and forth. So this kind of stories, yeah, so that will all work, yeah.
Okay. Yeah. Okay, thank you.
But what will not work is if you go and put a magnetic field in, then you leave the symmetry class, you go to symmetry class D, and we haven't managed to make the supersymmetric story work for that symmetry class.
Okay, so if I have say a Heisenberg-Kataev model with some off-diagonal exchange, then I shouldn't have, and then this will break down, right?
Well, that's a different one. So so that's just a very general Hamiltonian that is not necessarily be possible to describe by this Majorana Fermi decomposition in a well solvable, meaningful way. You will have interactions between the Majoranas, and then you have to be very careful about calculating how Poisson gaps close and what the Majoranas interact with and all these things. Yeah. But what I mean is if you put a magnetic field, that will surely it will break time reversal symmetry, and that changes the symmetry class. Yeah. And everything we have done here, was actually building on the fact, that time reversal symmetry survived, the SUSY operation, the supersymmetry step. So what has been supersymmetric in the fermions is all. So what has been time reversal in the fermions is also time reversal symmetric in the bosonic degrees of freedom. And well, we know that time reversal symmetry is very important, in stabilizing, these topological insulator states, and that is why these states go back and forth, and that's that explains why topological mechanics works, yeah, because it has the same symmetry, yeah, protecting this topological state.
Okay, thank you. Any other questions?
Yeah, I had one question. So in the case of the higher order topological insulator, I guess there's understanding of these phases is SPTs protected by lattice symmetries.
Yes.
And I'm wondering if the Berry curvature, the bosonic Berry curvature, requires lattice symmetry in order to be quantized.
So yes, so that was all actually built in. So let me show you. So here, so in this, here are the symmetries, that this lattice has, yeah, and that actually protects, this these corner modes. Yeah. And by going to the mechanical system, yeah, so you see that this is basically a square lattice. Yeah. So it's slightly distorted just for visual, but topology, it's just a square lattice. On the next slide, I showed you exactly the same thing. So it's a square lattice, and also, the spring model has exactly the same type of lattice symmetry set to put in on the fermionic side. So that didn't go away.
Yeah, but I guess can you see if you break, like, say, a reflection symmetry, that you can tune the corner mode away, and also tune the Berry curvature to the non-quantized value?
So the honest answer is I assume so. We haven't tried. I don't remember maybe we tried. But it should be that way. Yeah. So you're right. Yeah?
Right.
So
I see.
Yeah, so if you take away that protecting symmetry, so it's like time versus symmetry. It survives, the SUSY operation, but so if you steal it, that topological state should go away. And one can look. So that should be the case here as well.
Yeah, cool. Thanks.
Okay, so if there aren't any more questions, then maybe let's thank Professor Trebst again.
Thanks, guys.